What is interrupt latency, and how do you manage it in embedded systems? Imagine you're playing a game where quick reactions matter. In electronics and embedded systems, the speed at which your system responds to external signals is just as important. That quick response is what we call interrupt latency. Now, what exactly is it? Well, it's the time delay between when a hardware device sends an interrupt request and when the processor starts executing the code to handle that request. Think of it like a quick tap on your phone to wake it up. The delay is how long it takes for the phone to respond and show you the notification. In embedded systems, this delay can be the difference between a smooth operation and a missed critical event. For example, in motor control or sensor data collection, responding fast can prevent errors or damage. The length of this delay depends on several factors. First, the processor architecture plays a role. Some microcontrollers are designed to acknowledge interrupts faster than others. Next, the interrupt controller, which manages multiple signals, can add some delay depending on how it's built. Another factor is what the processor is doing at the moment. If it's busy executing a long task, it might take longer to respond to an interrupt request. Also, if the system disables interrupts during critical sections of code to avoid conflicts, that can increase latency. The priority of interrupts matters too. Higher priority interrupts can preempt lower priority ones, which can reduce the delay for urgent signals but might cause longer delays for less important ones. Managing this delay is essential for real-time applications. One way to do this is by choosing hardware that is optimized for quick responses. Microcontrollers with dedicated hardware interrupt vectors can jump directly to the ISR or interrupt service routine without extra delay. Setting priorities for different interrupts ensures that the most important signals are handled first. You can also enable nested interrupts, allowing higher priority signals to interrupt ongoing ISRs, which helps reduce worst-case latency. Keeping the code that disables interrupts very short is another key step. This means only disabling interrupts during tiny critical sections, so the system can respond quickly outside those periods. Making the ISR itself efficient by saving only necessary registers and keeping the code short also helps. Using a real-time operating system can give you predictable response times because it manages tasks and interrupts with strict scheduling rules. Finally, designing ISRs to do only quick, essential tasks and deferring longer processing to background threads or tasks keeps the system responsive. This approach is especially useful in applications like sensor data collection, motor control, or communication protocols, where timely responses are vital. In summary, interrupt latency measures how fast your embedded system can react to external signals. Managing it involves hardware choices, prioritization, minimizing disabled periods, and using efficient coding practices. When done right, it keeps your system responsive, reliable, and ready to handle real-time challenges.